So it turns out that the author of our notes, Dr. Shalia Harris-Plant, has already made videos for all of the examples in our notes. So I think instead of me just going through the examples like we do in a normal class, what I've decided to do is I'll share her example videos with you, and instead what I'll do is I will make a short summary video for each of these sections of notes that we're going to talk about. Now, I want to emphasize that this video is not meant to replace reading the notes or going through all of the example videos. I still want you to do that, but I'm hoping that this short summary video will help you to understand sort of the goal for each section of the notes. And maybe revisiting this video after you've gone through some of the examples will help you to sort of understand this unit and pull everything together. So the first section of notes that we're going to look at is characteristics of polynomials. And we've already met these four polynomials, so we know what the graphs of x squared and negative x squared look like. We also know what the graphs of x cubed and negative x cubed look like. So we know these graphs already. The goal in this section is to determine what the graph of a general polynomial looks like. And in order to do that, we are going to focus on two things about the polynomial. We want to know what its end behavior is, so maybe I'll write these down here. The two things that we care about are the end behavior and root behavior, or zero behavior. So those are the two things that I expect us to be able to graph for a general polynomial. And let me just mention that a polynomial looks like this. So polynomials are things that look like some number times a power of x, or linear combinations of those things. So this, for example, would be a perfectly good polynomial. Maybe let me add a couple terms here. So maybe let's say you have something like this. That's a perfectly good polynomial. It's a linear combination of powers of x. Notice that these last two terms are also powers of x in a sort of weird way. X is just x to the first power, and then 7 can be multiplied by x to the 0th power, because remember, anything to the 0th power is just 1. So this really is just a descending set of multiples of powers of x. So remember that we have this terminology that we use for the highest power here. We would call that the degree of the polynomial. So this is a degree 4 polynomial. And we also have a word for the coefficient that's attached to that highest degree term. That's called the leading coefficient. So the leading coefficient here would be 7. So the first thing that we're going to focus on is determining the end behavior for a polynomial like this in order to be able to graph it. And the important thing about the end behavior can be summarized in these four graphs that I have up at the top. So it turns out that the end behavior only depends on the degree, which is the highest power that shows up, and the sign, so positive or negative, for the leading coefficient. So notice that on the left side here, I have a positive and negative leading coefficient with even degree, and then on the right side, I have a positive and negative leading coefficient with odd degree. And it turns out that the end behavior for these pictures is going to be the same as the end behavior for any sort of general polynomial, with the same evenness or oddness of degree and same sign for the leading coefficient. So in this particular case, what we have is an even degree and a positive leading coefficient. So I can come up here and I look for the picture that has an even degree and a positive leading coefficient, and that would be this one. Because here I have an even degree, the degree is 2, and a positive leading coefficient. The lead coefficient here would just be 1. And what this says is that the end behavior for the graph x squared will be the same as the end behavior for this polynomial that we're trying to graph down here. And what I mean by end behavior is just what the graph looks like on the far left side and on the far right side. So I'm not really talking about what the graph looks like on the interior here. I'm just talking about what it will look like if we go to the far left side or the far right side. So what we've just seen is that the lead coefficient test for this particular graph will tell us that this polynomial's graph will go up on the far left side and up on the far right side, but we don't really know what this polynomial looks like on the middle here. So we're not going to worry about that for now. That is how we determine the end behavior, and you'll see several examples of that in this section of the notes. But in order to fill in this interior portion of the graph, what we're going to focus on is the root behavior, and that's what the polynomial does at each of its roots. Remember, a root is a 0 for the function, which is the same thing as an x-intercept. So in the picture that I've drawn down here, you have 4 roots. Those are the places where we cross the x-axis. Those are the zeros for the polynomial f. Now, the root behavior is most easily determined whenever you can factor the polynomial fully. So maybe let me just review an example where we know how to factor the polynomial. So let's think about a polynomial like this. F of x is equal to x cubed plus x squared minus x minus 1. So we're focused on the root behavior for this. And in order to figure out the root behavior, what I'm going to do is I'm first just going to try to find a root. And then once I identify a root, I can use the division theorem that we talked about in the previous set of videos to start factoring this polynomial. So we're looking for something that we can plug in to cause this polynomial to spit out a 0. Now in this particular case, there's something kind of convenient, which is that if you add up all of the coefficients here, you get 0. So notice that the coefficients here are 1, and then a 1, a negative 1, and a negative 1. If you add up 1 plus 1 minus 1 minus 1, you get 0. And that just means that if you plug in a positive 1, we're going to get 0. So this would be a 1 cubed plus a 1 squared minus a 1 minus another 1, and this will be 0. So in other words, anytime the coefficients all add up to 0, that means that 1 will be a root of the polynomial. So 1 is a root. And remember that 1 is a root if and only if x minus 1, in other words, the linear factor with that root, divides f. That's what we saw in the previous lesson. And what that means is that our function f of x can be written as x minus 1 times the original f of x divided by x minus 1. In other words, I can split this into 2 factors. One of them is the factor that we just extracted, and then the remaining factor will be the original polynomial f divided by x minus 1. So let's compute this second factor just to sort of review how that goes. So we'll do this with synthetic division. So if I wanted to divide f of x by x minus 1, I would put the root out here, and then I'll put the coefficients for f on the inside. So those coefficients would be 1, 1, negative 1, negative 1. And then we'll just go through the synthetic division process. So I bring down the first number, and then I multiply it by the root. And then I add in the next column, multiply by the root. Add in this column, multiply by the root. Add in this column. Remember that this last number represents the remainder, which we know is 0, and then this is the quotient. So what we've just seen is that the original polynomial f can be factored as an x minus 1 times an x squared plus a 2x plus 1, because that's what we get as our other factor here. So this gives us a way of factoring the original polynomial f that we started with. And now if we're just looking for all of the roots, we could notice that the root here is a positive 1, and then we could identify the roots for the second factor by just using something like the quadratic theorem or whatever. We could also just directly factor this if we wanted to, because it is a monic quadratic. So we're looking for 2 numbers that multiply to give us a positive 1 and that add up to a 2. And those factors would be a 1 and another 1. So in other words, I can continue factoring this as an x minus 1 times an x plus 1 times another x plus 1. So notice in this case I have a repeated root. So we ordinarily are going to write the repeated roots like this. We'll just put an x plus 1 squared because that factor is repeated twice. So in this case, there are 2 roots the roots are 1 and -1, because this first factor has a root of 1 and the second factor has a root of -1. But notice that they appear a different number of times in the factored form. So we call that a multiplicity. The multiplicity of this first root is 1 because that factor appears just once in the factored form. So the multiplicity of 1 is 1. But the multiplicity of -1 is a 2 because that factor appears twice in our factored form. And it turns out that this multiplicity will affect the graph. So remember at the beginning of this video what I mentioned was that there are two things that we want to include in our graphs. We want to know the end behavior for the graphs, which is what we talked about at the beginning, and then also this root behavior. So now let me talk about what the root behavior is. Notice that in all 4 of these pictures, there's just a single root or a single crossing for that x-axis. Maybe I should say a single touch of the x-axis. So all of these just touch the x-axis at 0. The difference is that 0 has a different multiplicity on the left side and on the right side. So on the left side, these polynomials, you can think of them as an x minus 0 squared. So that would be the linear factor with the root 0, but it appears twice on the left side. And that factor appears 3 times on the right side. So this is the last distinction that we're going to talk about in terms of the root behavior. This is again dependent on the evenness or oddness. So if you have a linear factor that appears an even number of times, then what happens at that root is the graph will just bounce off of the x-axis. So it does touch the x-axis, but it's a bounce. And then conversely, if you have an odd power for that linear factor, that would be an odd multiplicity, and that will represent a crossing of the x-axis. So notice that in both of these right side pictures, we actually cross the x-axis rather than bounce off of it. So let's put that together to graph this polynomial down here at the bottom, and then I'll let you get started on the example videos. So notice that from the first form of the polynomial, we can already determine the end behavior. The end behavior for this graph is determined by that highest order term, so that would be this one. That has an odd degree and a positive lead coefficient. So I can scroll back up and look at the picture up here that has an odd degree and a positive lead coefficient. That would look like this one. So the end behavior will be down on the left side and up on the right side. So in other words, the graph of this polynomial will look something like this on the edges. But now we need to fill in the interior of the graph. So I'll do that down here. We know that the graph looks like this on the edges, but we need to fill in the interior. Now we found the 2 roots already. We know that at -1 there's a root, and at +1 there's a root. Now let's look at each of these roots separately. So maybe let's look at -1. So we saw that -1 had a multiplicity of 2. So that's an even multiplicity. And what we saw earlier is that whenever you have an even multiplicity, that's going to represent a bounce in the graph. So this will still be a root, but the polynomial will bounce off of that point. So it still counts as a root. It is an x-intercept, but will bounce off of the graph there. And then whenever we come to this other root, notice that the root at +1 has a multiplicity of 1. That will be a crossing of the x-axis. So the graph of this function will look something like this, very roughly. So that's what we end up getting for the graph of this function. And that's sort of the goal in this set of notes, is just to be able to generate rough graphs of these polynomials. Now, you can make the graph a little bit more precise if you wanted to by just plugging in particular points. So for example, I could figure out the coordinates of this point by just plugging in x equals 0 to figure out the y-intercept. It looks like if I plug in x equals 0 in this polynomial, I would get a -1. So another point that belongs on this graph is 0, -1, and you could do that for other points as well. So you could plug in something like 2 to figure out what the point above 2 would be. But all that I'm focused on in this set of notes is just figuring out the end behavior, which is what the graph looks like on the far left and far right, and then